Good morning, everyone. Welcome, and thank you for joining our webinar today. My name is Patrice, and I'm the Marketing Director at MMT. We're an end-to-end medical manufacturing equipment and solutions provider. Today's webinar, we're discussing improving efficiencies and quality through automation of secondary processes. And in order to present in a timely manner, we set aside 10 minutes at the end for Q&A. Please feel free to type your questions in the chat and we'll answer accordingly. Today's presenter is Crew Feighery, VP of Catheter Technologies at MMT. Crew began his career with Cineo, a division of MMT, in 2010 as an applications engineer. His career with Cineo, he's held positions at Cineo in engineering, sales engineer, director of international business development, and director of sales. He holds a degree in mechanical engineering with a specialty in materials from the University of Central Florida. As Catheter Technologies VP, Crew now leads the technical sales team for MMT, each of the 7 catheter technology business units, and he helps customers and provides them with holistic solutions to their manufacturing challenges. And when he's not in the office, you'll find Crew spending time with his wife and 3 small children, or flying the skies of Central Florida in a plane he built. Without further ado, please welcome Crew. Crew, the floor is yours.
Perfect. Thank you, Patrice. Yeah, so a little bit of background about me. So good to hear. Thanks everybody for joining. Really appreciate your time. Today's presentation is going to focus on improving efficiency and quality through automation of secondary processes. And really, when we talk about secondary processes, what we're talking about is anything downstream of extrusion. We're talking about minimally invasive medical devices, primarily catheters and guide wires, things of that nature. Those are the types of devices that we're going to focus on. First slide we'll talk through is just a little bit of background about who MMT is to make sure that you know who we are and who you're hearing from. So Medical Manufacturing Technologies is the parent company for several smaller companies underneath its umbrella, with a core focus on service in the medical device industry around capital equipment. So if you think about the 3 main tiers or kind of legs of the stool for MMT, we focus on catheter technologies, grinding technologies, and automation. And then if you look at each one of these cells around the logo, what you'll see is the individual business units that they represent. So they're in alphabetical order, but what you have here, so cath tip is known for RF tip forming, so for catheters, and as well as coated guide wires. They also do hole forming. Engineering by Design is a company based out of San Jose, California, that does vertical reflow lamination as well as coil winding over discrete mandrels. Glebar does centerless grinding, microcenterless, and some other specialty grinding for med device and industrial applications. Interface Catheter Solutions does balloon forming, pleating and folding, marker band swaging, and everything really around the business end of that catheter. Medical Production Technologies is based out of the Netherlands. It also has some very high-end balloon forming equipment, pleat and fold, as well as thermal bonding. MMT Automation was previously Ward Automation based out of Ireland, and they focus on general automation around medical device manufacturing. Tridix Technology is electrochemical grinding. It's a very neat solution that's a mixture of both mechanical grinding as well as an electrolysis process to give you a burr-free cut. Great for hypotube cutoff or for grinding of hypodermic needles or trocars or things like that with a burr-free edge. R&D Engineering is based out of Minneapolis. They are known for vertical reflow lamination, curving systems, mandrel pulling, liner stretchers, so things around that catheter shaft manufacture. Somix Automation is another automation company well known in Ireland around medical device manufacturing. And then Cineo, where I started, in 13 years now, was known for automatic cut to length feeding for catheters, guide wires, things of that nature, as well as hole forming and feeding into various applications downstream. So ultimately, Medical Manufacturing Technology is a vertically integrated business serving the medical device manufacturing industry and beyond. So the agenda for today, I want to cover is really just a general presentation around if you're going to scope automation, if you want to automate your processes, some things to think about that are going to make your life easier. It's really just going to be general, not a sales pitch at all. It's things that should be helpful for you as you think about what your opportunities are for automation in your manufacturing floor. So for me, the best place to start, kind of figure out where you're going, is to figure out where you started. So I'd want to touch on the PTCA balloon catheter first. That's really the first complex catheter that was developed, and we'll talk through how it was developed and why. And what that will roll into is what the current state of the medical device industry is based on where we've been, kind of where we are now. And then as we look forward, one of the things you hear a lot about when you're talking about automation is Industry 4.0. So basically, are we there yet? When are we getting there? The next place we'll look at is the factory floor map. It's a neat infographic that we've developed to kind of visualize where your process is on the factory floor. So you can think about looking upstream and downstream of your process and look to start combining processes. And then we'll move on to how best to identify processes for automation. So just because you have a process that's difficult doesn't mean automation is the answer. So we'll touch on that. What should we be looking for? What are the ones that we should be trying to automate? And what are the ones that we should, probably pass on and just keep them more of a manual process. And then once you've found those processes you want to automate, what are the mistakes that you might make when you're trying to scope the automation to a vendor? Ultimately, you need to be able to articulate what it is, what the challenges are, what your needs are, and try to communicate that to a vendor who can then develop a piece of automated equipment for you that ultimately you're happy with and they're happy with. And then once that machine has been delivered or the system's been delivered, it's about how do you make sure that that system's going to run for you long term. So talk about just keys to successful long-term automation and what you should be doing, how you should be training, how you should be maintaining things of that nature. So what I hope to do in that whole exercise is walk us through kind of, again, where we started, where we're going, and how to continue to improve into the future. Looking out to a faceless audience, so hopefully everybody's entertained. So where to start? So the PTCA balloon catheter, where it all began. So PTCA, what that stands for is percutaneous transluminal coronary angioplasty. Essentially what we're saying is that we're going through the skin, we're going through the arteries, which is the lumens inside of your body, the coronary area, which is the arteries that surround the heart, and the angioplasty is the surgical repair, unblocking of a blood vessel. So in the simplest terms, the most common issue that we see is that angina or that blockage in the heart, where we need to go in and we need to open it up, possibly place a stent. So obviously the animation that we see repeating here is the typical balloon catheter where it's placing a stent into a blocked artery. But what's very interesting is kind of where this all began, and it might not be as long ago as you might thought. So looking at this bottom left corner, what you'll see is the very first balloon catheter that was ever developed. It was developed in 1971 by a doctor named Andreas Grunzig. He was he was from Germany originally, and he developed the first catheter while he was in the UK. The next thing to look at is really the very first catheters for use being developed and manufactured in a kitchen. You can see the bottle of wine there. So obviously the scope or the SOP for building catheters changed a little bit over the years. But what they were actually doing was they would measure the arteries of the patient that they were about to give the procedure to, and they would determine the length and diameter needed, and then they would actually make these parts one at a time. Make these catheters one at a time to use in the process. And what's interesting here is they've taken a standard catheter they would be able to find. They actually put a piece of an elastic tubing over that. They tied it with a yarn. And now what they're able to do is obviously inject the saline solution or a fluid through it and inflate that balloon. So the thing to note for most of us is obviously this is a single lumen catheter. It doesn't have the same lumen that we would have for guide wires or navigation. But so single lumen, go in there, blow up the balloon, open up the blockage, pull it back out, and hope for the best. But this was really a groundbreaking technology and procedure they developed back in 1971. And then what you can see is as the technology progressed, now we start to land at something that we're more used to seeing. So this obviously before with all the injection molds and that we have now for the stock cocks, the lure locks, and some of the tubing that were previously metal, previous to how they're developed. Then now we've moved into this dual lumen plastic catheter, more of a standard balloon form factor that we would see. So we're starting to get to what we'd expect to see today. That's where it all started. Now you think, okay, this is how it started, right? It was on a nice lady's table. She's manufacturing the catheters, a bottle of wine, and now surely, 50 years later, we must be in a fully automated type of setup. Well, the truth of the matter is, we all can walk out to our manufacturing floors and see exactly how these parts are made. So it's in a clean room. There's no wine to be seen. And obviously, but it's just still a bunch of people around tables building these parts one at a time. And that's really the challenge for med device, especially in this minimally invasive space, is how do we go and automate a process that historically was developed for, manual assembly by almost skilled artisans in a lot of cases, depending on the process. How do we now go and automate these tasks? That's the challenge. And now we think through the Industrial Revolution. So when people talk about Industry 4.0, what they're talking about is just this place where we are, where they want to be, right? Some factories are out there are Industry 4.0. What does that mean? It's a smart factory, it's autonomous, you have automation, it's the things you think of, but really what it means, it's machine learning. It means that it can make a part, it can look at that part, it can determine the flaws, and then communicate that back upstream into the process to try to make an improvement over time. So what that relies on is obviously automation. It relies on the data gathering, and it relies on your input materials being extremely consistent, where you can go back and make a small tweak or a change to the process and have an effect downstream when the part's completed. So when we think about the industrial revolutions, obviously Industry 4.0 or Industry 1.0 was the mechanization and using steam and water power, right? It's having power to make these things. 2.0 was mass production assembly lines using electric power. So now what we can start to think about is, the two main things that people think about in terms of automation or scale manufacture was originally the Colt Dragoon revolver. What this was is it was a gun that was able to be produced at an inexpensive price because the parts were interchangeable. So this is really that first mass production assembly line product that was able to drive down the cost of something that previously was made by an artisan, was made by a gunsmith. And then the second one that we think about is the Model T Ford, right? That was the car for the people. And the reason for that was because they were able to make it at mass quantity with its scales of economy, right? It's being able to have the same parts, being able to assemble it on an assembly line and bring it all together. So that was 1913 for the Model T. It was 1848 for the Colt Dragoon revolver. And then the modern PTCA catheter, as we talked about in the previous slide, it was developed in 1971. So surely, 100 years after the first revolver and 60 years after the Model T, we must be able to automate this process, this catheter manufacturing process. But the truth of the matter is, when we really look at the industrial revolutions, we're somewhere between Industry 2.0 and Industry 3.0. We have a little bit of automation. We do have IT systems that are helping us a little bit, but the vast majority of it is really Industry 2.0. And even previous to that, because we do have so many artisan processes. It's not, we all know that we can't just take a bunch of parts from any part of the assembly line and bring them together. It's really handcrafted, and these materials and products are they're just handmade. So when I hear about Industry 4.0 and the med device space and what we're talking about, it's I do chuckle a bit, because we're really, like you said, we're somewhere here between Industry 2.0 and 3.0, and really in some cases we're even lower than Industry 2.0 based on the being able to utilize the same parts across different products. So now we know kind of where we began, the history of the automation, and now we say, how do we identify processes that are suitable for automation? And if you think about, again, we're talking about the minimally invasive medical device space, you can really categorize the vast majority of products into three primary types. The first in the top left is going to be the traditional guiding catheter. So, PTFE or lubricious liner that then has been braided over, and then with a reflow jacket on top of that. Obviously, with different products, you're gonna have different durometer changes as it gets closer to the tip. So again, this is it's a pretty simple device when it's all said and done, but lots and lots of time and effort is put into this. And the challenge is it's the way that it was developed and the way that these things are made. It makes it extremely difficult to try to automate from start to finish. Now there are some sub-assembly processes or some things that you can do and focus on a bit of automation. But ultimately, when if we think about the lamination process of stretching a liner over a mandrel and then feeding it through a braider and then putting a jacket on it, loading up PBAX pieces one at a time and putting heat shrink over that, it's just a very manual process. So that one has its challenges. And then we talk about the guide wire process. So this is an example of a quite complex guide wire that also is similar to like a stylet that you would see, where you're going to have a core wire, you're going to have a coil over the top of that core wire that's been bonded to the core wire in some way. It might be a glue, a UV adhesive, or it might be a solder or a laser weld, some different technologies there. And then that wire is going to run through. You're going to have a profile on the inside of that wire. That's meaning it's been ground down to some different shape to either make it more flexible or to make it biased to one direction when it turns. And then you need to bond everything together at the tip. So this is a more complex guide wire. Definitely some opportunities for automation here, especially when you talk about feeding and handling and grinding and some of the other things that you can do. The sub processes, but the final assembly really maintains to be a very artistic process of bonding that coil to the core wire and the coil and the core wire to the tip. Quite a challenge. And then the last one, this is getting more to that complex catheter. So this is a pretty typical coronary artery angioplasty catheter. It has the stent on it. So essentially what we're going to do here is it's going to go into the body. It's going to inflate and it's going to deploy that stent into the area where the blockage is. But if you look kind of down the length of the shaft, what you see is this atraumatic tip that's been bonded on. That's typically going to be done with RF. You also have bonds on each end of the balloon to bond it to the shaft. You have marker bands underneath the balloon that need to be swaged on. Of course, there's the stent over the top of the whole thing. And during the process, this needs to be pleated and folded and made as compact as possible so that it can deploy into the body. And then you have the actual catheter shaft. So that's going to be some sort of a composite design that's going to go from a braid or a coiled shaft to a non-braided section at some point. It's been built up in a myriad of different ways. You're going to have holes in it that allow you access to certain lumens, things like strain reliefs, and then hubs that need to be glued or bonded onto the catheter. So today, what we're going to focus on is really this complex catheter. And then again, there's far more complex catheters out there than this, but this is a good analog to something that we would see on a regular basis. And there's some opportunities for automation along the way. So when we look at the complex catheter, what we've done is we've kind of mapped out what your factory floor would look like in terms of what equipment you would need along the way. To be able to produce this device. And again, this is thinking about that balloon catheter that we just saw on the previous page. So what you can think about is your raw extrusion or liner coming in. You're going to do some braiding over the top of this system. You're going to then feed and cut all the individual PBAX components that are going to go over the top of that one. You're going to reflow those parts. You need to remove the mandrels. So you're going to pull those out. You're going to cut that braided catheter to length. Now you need to bond on the soft tip with an RF bonding system. And then once you've done that, you really would like to test the jacket to make sure that you don't have any exposed braids, whether when you do the reflow process that it didn't squeeze down too hard and leave a thin spot in the PBAX jacket and then cause you to have an exposed braid, or in the area where the bond goes from braided to non-braided to make sure that one of those wires didn't flare out on you and come through the surface. So there's a high voltage test, non-contact test that you can do to make sure you don't have any exposed braids. You might do some printing or some laser marking on that product. And then you're going to move it. Now you have the main catheter shaft. You're going to move through into, now I need to do the balloon forming. So I'm going to blow the balloons. I'm going to do pleat and fold. I'm going to do pressure testing and inspection, and so forth. And then now I have the balloon, I have the catheter. I need to bond these together. So what I'm doing here is these are the different components I may need to get me through, where I'm going to do pre-swaging and swaging of the marker band. I'm going to make the holes for the inflation lumen to come through underneath the balloon. I'm going to do some different bonding. I'm going to do some different testing. And then finally, it's going to leave and head out for sterilization. So a common theme would be for any one of us is to walk out on the factory floor and say, where do I begin? How should I start this? How should I automate this process? And I think the first thing to note is that until we design a product that's better for manufacture, so designed for manufacturing from the beginning, we will never be able to fully automate this catheter manufacturing process. But we can take a lot of labor content out of it by automating certain processes and combining other processes. So when we think about how should we be identifying processes that are suitable for automation, so the first thing to think about is my current process repeatable, right? Meaning, if I have the same person do the same thing to the same material every time, am I going to get the same result? Because ultimately what automation is it's taking your input state of the material, it's assuming that they're the same every time, and it's running the exact same process to it. So the thing to know about automation, it's going to do the same thing every time. And if your input material is varying, then your output condition is going to vary as well. The next thing to think about is a repetitive task, right? So you might have a simple repetitive task that you have many people doing, one person doing, but all day, every day, they're doing that same task. And there's some opportunities there just for simple automation, whether it's pick and feed, feed a part in, feed a part out. The thing to think about for automation is we like to think about big, fancy, all-encompassing automation lines, but keep in mind that just automating one or two processes can pay dividends in terms of throughput, yields, ergonomics, all the things that you'd like to see improvements on. Other thing you're looking for is high volume. Like that's the challenge that we face in med devices. Most of what we have is it's low volume, high mix. What you would love to find, of course, is the high volume, low mix in terms of part numbers. So these are things to look for. And don't just think about part numbers in terms of, hey, I have 1,000 different discrete part numbers, but really it's product families, right? I have this many different products that are within this diameter range and this length range. If you can start to put bookends on the variables for your devices, you can start to categorize these or kind of put them into families where, hey, maybe this family is really suitable for automation because there is enough similarities between them. So one of the challenges I've faced with customers in the past has been, they're focused on, we want to automate the entire process. We want to automate all the part numbers. And what you end up with there is, what you don't want with automation is a Swiss Army knife when it's done. It can do a lot of things, but it can't do anything very well. What you want to focus on is keeping the core technology efficient and robust so that you have a great process to use. And then the next piece to look at is combining upstream and downstream applications. I think this is where this particular map is very helpful. And I'd encourage you to do the same with your current factory floor. Look at it with a fresh set of eyes in terms of, how is my factory floor laid out? What are the processes that need to happen? And then do they need to happen in that same order, right? So that's one of the things I mentioned here is don't be forced to keep the same process flow. And one of the boxes you get stuck into is you say, well, this is the first step, and then this, and then this, and then this. But the challenge you face is that a great example is as soon as you put a hub onto the back end of a catheter, you can no longer pass it through an automated system because you have a large diameter and plastic hub that's hard to pick and feed and move through a system. So if you, for example, were going to put a hub on in the beginning of your process and you're basing everything on that hub to be your datum for the tip, in the future, the problem is you're putting your material on and then you're bonding something and you're making holes and everything's datum from that hub, which is understandable. The challenge that you face when you want to move that into automation, though, is that if you didn't have the hub on there, you could do all those tip processes potentially automated and then put the hub on at the end. So don't always assume you have to keep the process flow the same. And part of the effort that you put into saving time and money and efforts, like, yeah, there will be some work into maybe revalidating a process or proving out that it should be done in a different sequence. But ultimately, for the long run, you end up with a much more efficient process. Then the last thing to think about is material input form, right? So raw material, talking about extrusion, plastic tubing, it's going to come in two forms. It's either going to be on a spool or it's going to be in sticks. Obviously, for automation, the form you would always wish to have the material coming in from is a spool, because you only have to find and capture the end of the material one time. Whereas sticks, you have to pick and feed individually. Now, for our industry, we know and understand that the challenge you face is that as soon as you put material on the spool, you have coil set on that spool or on that material, and that's just not suitable for the finished product. So it needs to be in sticks. But to think about the fact is, where do I need actual sticks of material? Where can I get spools of material? Because you know that that's going to make your process more automatable and more robust long term. So that's how we think about kind of looking at the factory floor map. I'd encourage you all to do the same, map it out, look for areas that you can combine, look for different sequences. You could do things that would allow you to have it make more sense from an automation standpoint, because it's just going to make your life easier. So here what we have is an example of a neat little demo system that we have. I wish I could show you all the automated systems we built for customers, but IP kind of protects us there, protects the all of our customers. We want to make sure we're being cognizant of that. So this is actually a system that we developed for a trade show. One of our business units, Catheter, this was a system that they had built to show off a combined system that's going to do hole forming, tipping, and inspection. And I think what's really interesting here to look at is it helps to highlight a few things that might seem obvious at first, or maybe not, but why this particular operation is suitable for automation. So the first one, of course, was it was a dedicated application. This is doing kind of a mock dilator, where it's a fairly rigid material, not super long. It's a pretty straightforward diameter, able to be picked and fed without much problem. And what we're doing is we're saying, hey, we have this nice material. We can pick it up. We can feed it into the drilling system. We can make some holes along the way. Then we can take that, we can dip it in a little bit of mold release there, we can load it into the system, and now we can actually run this process automatically. So the thing to look at here is what we're doing. We've actually automated around manual processes and standard machines. So utilizing some off-the-shelf robotics and then making some end-of-arm tooling and whatnot. So this is a pretty simple demo, but again, the idea here is you're looking at what can I do to combine processes? How can I pick something up, feed it into a machine, feed it into a second process, and then do some sort of inspection downstream? One thing that we'll touch on in a moment that's worth mentioning now is that you can't overlook the inspection factor when you're scoping automation. What you have with an operator, regardless of how menial and basic the task is with a human comes a pretty incredible set of sensors, right? In your eyes and your fingers and the tip and what you feel. So if a part's being run in a tip forming system and I go and I load the part in and I pull the previous part out, while that next part's running, I'm running my fingers over it, I'm looking at it, and they're able to catch issues that are happening in real time. So one thing to keep in mind is anytime you're going to scope automation, it's critically important that you also think about including the proper revision or inspection along the way, because as soon as you pull that operator out, you just lost a vision system. So it's just something to keep in mind. So now let's talk through some common mistakes when you're scoping automation, right? So you've walked through your factory floor map, you've developed a couple processes that you would like to see automated. You've got kind of a rough scope of work of what you want, but what are some of the mistakes that you might make along the way? So the first one we talked about before is most med devices, low volume, high mix. The biggest error or problem that we'll see when customers are scoping automation is they say, we must automate 100% of our part numbers or we just can't do it, or it's just not worth it. The truth of the matter is, though, again, when you put things into product families, when you start to look at similarities, what you're looking for is the tried and true 80-20 rule. Look for the 80% of your parts that fall together that are automatable, and leave those 20% to continue to be a manual process. That's one of the hardest things that most people have to overcome, or some of the hardest things that we try to sell to our managers internally is, hey, I have this process, I'd like to automate it. I can't automate everything, and it kind of just dies on the vine right there. And in reality, most of what you do, a huge volume of what you do, might be able to be automated, and it's worth doing and keeping a few processes manual. Second kind of rule is don't try to tie too many processes together, right? It's easy to look at that factory floor map and you get lots of customers will come to you say, hey, we want to combine these 10 processes into one system. And the thing you have to remember is every time you add an additional process, you've added almost a additional order of magnitude complexity to the system, because now what you have is, in just thinking through, it's like, so you have to have, let's call it 3 robust processes that have to run perfectly. And now you want to add a 4th. Well, the challenge that you have is that any one of those, so any one of those give you any issue, any one of them go down. Now you have all these processes tied together, and you may have scenarios where they won't even use all the processes. So it's not uncommon for somebody to say, hey, I want to automate these 4 processes, but this part of my product family, they don't need this one process, and these ones don't need that one. So again, the common issue that you run into is somebody wants to, I want to put everything in there and I want to do all the processes in one machine. What happens is then you don't have the ability to work offline. You don't have the ability for reworks. You don't have the ability to run in parallel for a process that might only need one of them tied into the entire automated system. So just keep that in mind. This is a good one. So review drawings and QC tacit knowledge. One of the biggest things that we see when we receive a URS from a customer, we start talking through a project, is we'll get the drawings and then we'll look at the specs. So we'll say, you know, this looks a little tight. Are you sure you guys are holding this to these tolerances now? Or this, you know, this process, this work instruction, I think that there's something that happens as you get into, you've done these parts for so many years, you have these operators who have been there, and you've started to see the criteria slip, or you've started to see it wasn't what, they're not being made exactly how they respect, and that's okay. It's okay for your finished products. But when you go and you automate a piece of equipment, you have to remember that, you know, you as the customer and also the vendor have to now hold ourselves accountable to those specs. So things that QC might have passed in the past previously, now that might fail because it's coming off of a machine. So there's some issues there. Anytime you bring a new process, people are going to be overly critical of what they're seeing. This one, already touched on that, right? Ensure you're manufacturing current work instructions, specifications. It sounds crazy, but we've definitely talked through some operations with the customer where they realized they weren't doing things the way they expected they were, and that killed some projects right there. I mentioned this one earlier. Be sure to include inspection. You know, your operators are passively doing 100% inspection. They might not be perfect, right? They have long days or they think about other things, but ultimately they're touching the parts, they're feeling the parts, they're used to seeing things, even in how the machine operates. They're used to hearing it run a certain way or hear a certain air cylinder move, and as soon as something goes off, they can pick up on it. So it's important to know when you talk about inspection, when you talk about downtime, when you talk about maintenance. These are things that operators start to learn inherently. Typically it's for the best, but sometimes that can be one of your challenges why you want to automate, is to take some of those out of an operator's hands if you see variability. But know that as soon as you do remove that, you need to make sure you consider that when you scope it out. Say, hey, we need inspection. Hey, we need to know if there's faults. We need to stop on 3 consecutive faults so that we don't have an issue with our process. Because an operator, if they're running a part, let's just say they're tipping a piece of material, they see you fail once, they go, huh, that's an anomaly. And they see it fail it twice, this doesn't look right. They see it fail a 3rd time, now they know they have a process. They're going to call a technician over, they're going to clean a mold, they're going to do whatever needs to be done. What you have to be careful for with automation is that you don't make something that's just going to make a bunch of scrap parts all day long. And in most cases, when you tie in that inspection, you're going to do that check every time, and you say that you can have that same thought process. First one, okay, anomaly, we're going to watch for that. We're going to spin that separately into a failed parts bin. Second part, okay, that's not good. What are we seeing? And then the 3rd one fails, and we're going to stop the system. We're going to throw up an error message and turn on the stack light and say, hey, come look at the machine. Something seems to be off. Talked about this one. Consider the part number versus product family. This is an interesting take on it, though. It's in terms of changeover times. So another thing to think about is the tooling changeovers, right? To go from one product to another, one part family to another, there is an amount of time it's going to take to set up for the next machine run. So one of the other challenges you face in our industry is that with that low volume, high mix, you do a lot of line changes or product changes during the course of the day. So what you have to start to think about is, I'm going to have to run these in more of a batch process, maybe one full, where I might used to change 3 times over the course of the day to different part numbers. I'm now going to put my focus on, I'm going to run one part number all day long, and then I'm going to change. So I'm going to minimize my amount of the changeovers, because that's going to save me in terms of the setup of with the tooling and dialing it back in and getting it up and running. No matter how good it is, no matter how turnkey and tool free and recipe based it is, there's always going to be some amount of time setting up for the next part. So it's just something to think about. And the common one there is if you think about diameter. So typically going from a shorter part to a longer part within reason, that's not too difficult. To change from one diameter to another diameter, that becomes more of a challenge in terms of the part path, because a lot of the tooling that's going to be guides and the tools that are used to guide that diameter, those are going to be the critical ones to make sure that you batch together. So in that case, you might want to batch based on diameter, things that are like in diameter over length. Just know that there's a lot of processes that can't be automated. Focus on the ones that can. Been in more than one facility where I've walked a customer's factory floor with them and made it back to the back corner where there was somebody weaving nitinol baskets under microscopes. There was a group of maybe 10 people doing this, and they say, "This is what I want you to automate." And you look at it and you say, "Hey guys, this is not something that's suitable for automation. It needs the dexterity of a human hand. You need a person to do it, but you just walked me past 10 other operations which are ripe for automation or semi-automation. Let's focus the attention on those. Focus on the low-hanging fruit, and then you can take and redeploy those operators to give yourself more people, more capacity, more ability to be able to work on those harder, more complex parts." So it's very common that somebody's going to focus on the area where the problem is, instead of focusing on where the low-hanging fruit is, so they can redeploy those resources to help in the area where there is the challenges. Keep in mind that your health and safety rules all. Make sure you consult them along the way. It's terrible to work through a whole machine build process, go through all the acceptance tests and make it all the way in, and then a machine goes into the factory, and then EHS says they don't like the height that something is, they don't like the layout, or it doesn't meet their safety requirements. So that's just something to keep in mind. Make sure you get all the critical parties in from the beginning, including facilities. Make sure hey, do we have power requirements or air requirements? Are there issues that we're going to run into if we try to automate this? Be sure to work through your URS and the FAT protocols of your supplier. Don't do it in a vacuum. What I would say is there's been plenty of times we've received URS and it ends up being something that effectively you have to no quote. And it can be just because of 1 or 2 bullets or requirements in that URS that make it impossible or not realistic to do. Or it can dramatically change the price of the equipment. So be open with your supplier when you're scoping this project, and say, "Hey, what are the ones on here that are no problem? What are the problem ones? What are the areas that are really adding cost or lead time to it?" So by adjusting the URS to kind of match the process and your supplier, you can really dramatically shift the price or lead time of a piece of equipment. And then on the FAT side, it's very important that you work with them to develop what's the correct protocol for when I come to you to run this equipment. What's the right quantity of parts I should run? What are the things I should be looking for? What are the things that I should be concerned about from a variable standpoint? Because if you've never seen a piece of equipment, it's hard for you to write an FAT document as the customer to come and go and test the machine. You might miss critical parameters, or you might not run enough. So just work with them. It's a partnership. And then also consider the future addition of part numbers. So it's not just what are you doing today, but what might you do in the future? Because something like, hey, we might have a part that's 2 inches longer in the future. It might not seem like a huge deal, but if we design an entire piece of equipment around, a 30 centimeter to 60 centimeter part, and then a year later you have a 62.5 centimeter part you want to put in it, sounds like it's no big deal, but but there's physical limitations within that system. So think about what's your min and max length diameters that you might ever want to run on it. Be realistic, of course. Don't try to capture everything, but do consider that and have those conversations early on so that you can utilize this piece of equipment on a future application. Yeah, so be cognizant of scope creep and lead times. So give yourself a buffer. I'm putting in here 15%. That's total rule, just um, off the tip of the tongue, what I'd say. But from your side, it's there's going to be things that you learn along the way. There's going to be things that cause you delays on a large scale automation project. You need to build in some buffer to your budget because what happens is you don't want to make compromises along the way. It's something that, you as the customer or the supplier wasn't able to consider because of the way it scoped out or the way it worked. But as you worked through it, you said, you know what, this is really great opportunity for us to add an additional inspection step, or this is a really great opportunity for us to add a little bit of length to the machine so we can handle a longer part. What can often happen though is you're boxed into a budget, totally understandable, and you're forced to either cut corners or pass up on things that would be useful to you in the future, or might make the machine better, more robust, etc. Okay, so that was how to scope. Now we've made it through. Machine's been delivered. You made it through the FAT. Everybody's happy. It's all good. Machine gets delivered to your factory. You're up and running. You're making parts. Now, how do I make sure that that automation is successful long term? Um, so this is thinking through maintaining it, maintenance, training, things like that. What are things you should think about? So first one we touched on previously, but obviously as it's delivered, your FAT, meaning at the factory that your supplier where you did the buy off, and now your site acceptance test. So as they come to you, it's critical, right? You want to make sure that you don't cut costs by saying, no, we only want to run a few parts or these part numbers or this quantity with the vendor on site. You want to run at scale. You want to run scale production. You want to work it through its kinks. You want the people around it to learn. The thing to remember is that the vendor has spent months developing and running this piece of equipment, learning a lot about it. They can run it, effortlessly. But your team, your engineers, your technicians need to learn that same thing. And actually being there running the machine is the best way to do it. Having the team that manufactured the system on site with you is critical. So run adequate volume, not just to prove out the process, but also to learn and understand the process and the equipment. Second one is to keep in mind machines are repeatable. Input material is not. Please be very wary of supplier changes. It's been, many times that you talk to a customer that says, hey, we've been using this piece of equipment for years. Suddenly it stopped working. We think the software changed, or we think this is wrong, or something failed. It's an obvious place to go where you say, hey, something's different than it was yesterday. It must be the machine's fault. The thing to keep in mind about automation is its inputs and outputs, right? It's not just in terms of material. It's also in terms of the actual logic and how it operates. It's a machine is going to do something until it hits some sensor, some input, and then it's going to do something else. So if it sees any change in that or can't run that exact same process, it's going to give you a different output and typically a failed output. So keep in mind changing from one PBAX to another PBAX. One, it can be durometer changes. It can be static electricity charges. It can be you change from single bagging to double bagging. You change from you used to inventory material in individual bags, and then you brought it out to the machine. You pulled it out and tried to run it right away. Static can be your biggest enemy in some cases. Versus other times you come in and you pull your material out. It sits out for a couple hours and the static's able to kind of dissipate. So just keep in mind that input material can vary widely, especially in our industry. If there's a problem, what did you change? What did the operator change? What's the last thing that you did? Walk back through the machine logs, figure out where it started going awry. Again, machines don't just change. The software doesn't just change. Typically, it's tied to some sensor setting or some variable that an operator or a technician or engineer changed because they thought it would make it a little bit better. And the issue there is you'll start to get this effect where you change it a little bit, you change a little bit more, you change a little bit more, you change too many things, and now you don't know where you started. And that's the one thing to watch out for. Be sure to cross-train operators, right? We all have operators in our building who are the machine whisperers of their particular piece of equipment. They're the ones who can make it run, and if they're out, then the production goes down and there's problems. This shouldn't be the case, right? You got to cross-train people. You need to spend the time and the effort to make sure that more than one person knows the machine, because it's just you need to set yourself up for success. God forbid they win the lottery and head out. Yeah, you need somebody there behind it that can run that machine. Bring in the automation provider for recurring training. This is a critical one that gets overlooked. So bring in the automation provider on a yearly basis or however often you need to do it to make sure that they're training your operators and technicians and engineers on not just what the machine does, but why the machine does it. Understand the theory of operation so that you know, hey, if I change this setting, this is what it means. The amount of time I've walked through, the variables on a HMI with a customer and they say, oh, I didn't know that that's what that meant. Or, oh, I was always told that this is what that meant. So when they were doing that, what happens over time is you lose that tacit knowledge. So the key here is to make sure you're getting the recurring training so you know what the machine's doing, why it's doing it, so that you can make those changes and updates along the way. And then kind of along the lines of what did you change, it's don't let the process parameters drift over time. Similarly, it's operators with sticky fingers that say, hey, I want to adjust this knob or change these settings. And it's important to know that all the critical parameters are always password protected, but there are some variables they can change, some sensor settings they could adjust, that over time they can start to drift. And you go from one setting to a little bit more to a little bit more. And again, you end up in a state where you don't know where you started. And so now it's a whole effort just to get it back to stock, to standard, to try to figure out what went wrong. So that's one thing, is don't let the process parameters drift. Make sure you document them, you track them, and check them on some regular basis. So make sure that those are all they're all tracked and logged. Properly maintain the machine sounds pretty straightforward, but the amount of times you see people, taping things together or kind of just barely holding the machine together, we have to keep in mind this isn't like your car. You don't drive it till it breaks and then have it fixed. You want to do preventative maintenance, more like you're changing the oil, because this is not your mode of transportation. This is your tool to make product and to make you revenue. This is something that you need to maintain. You need to spend the time and effort and money to maintain the machine, so that it continues to work as you need it to do. So preventative maintenance is key. Ensure that you receive turnkey documented applications. So again, this goes into some of the cost saving measures that you can have as a customer. As you can say, I have these 100 different part numbers, but during our FAT, or the URS is going to say, I want to run my low, my medium, and my high, to make sure it cover all the range. But what happens then, and that's because it saves you money on the applications development and the turnkey kind of recipes that can be saved in the machine by the factory. But the benefit of doing that and what you save in the long run of saying, hey, let's make sure you take the time and effort to develop recipes for every single application that I have. I want you to prove that it runs, and I want you to document, with what are the settings and everything. So you always have those to go back to. So many times you deliver a piece of equipment, it goes into a factory, they, you do your initial IQ, OQ, PQ on the system, and it wasn't done quite adequately enough, and you're going to be fighting that forever, right? It was qualified with a certain set of criteria, a certain set of parameters, and now you go to a facility, and you're like, well, why'd you set those parameters that way? We should adjust it just slightly higher or lower than your minimum or maximum allows. And they say we can't, because it's outside of how we've qualified the machine, and it was just qualified improperly. So be sure to have the automation provider help you develop the applications. That is the last one. So that gets us through. Again, just to kind of recap where we went, where we're going. So we talked through the PTCA balloon catheters. So where it started, kind of where we are, 1971, not that long ago, we developed the first balloon catheters, and here we are, 50, 60 years later, and not a whole lot in terms of automation. We talked through the state of the med device industry, Industry 4.0, walk through the factory floor map and how you should think about trying to identify different applications, and then look for those processes to be automated, how to scope them, and then what the keys are to successful long-term automation. So hopefully you found that insightful. I see Patrice pop back on. Got any questions?
Fantastic. If you have any questions, please enter them now. If not, we want to thank you so much for joining us, and we'll close out the meeting. If you need anything from us, please shoot us an email at sales@mmt-inc.com, or visit our websites. We have cineoco.com, MMT-INC, and you can submit a request there. I see the presentation is recorded. Yes, the presentation will be shared with attendees along with a survey, so please feel free to reply to that survey. That would be great. Is the presentation? Yes, it will be available. Anything else? No, thank you again for joining us. Have a fantastic day.
Thanks, everybody. Thanks, Patrice and David, for putting it on. I really appreciate it.
Thanks. Have a great day. Bye-bye.